Okay, let's give the jump a test. Whoa, okay, maybe that's a little too much. Hey everyone, I'm Pablo. This over here is Milo, and today we're going to do a tutorial on a third-person character controller. By the end of the tutorial, we'll have a character that can walk, sprint, jump, and overall have all the camera motion that you would expect. So this is just a foundation. Character controllers can get crazy complex, so this is more of a starting point. The main asset we'll be using is a free character pack from Unity. You can find the link down in the description. Create a new 3D project and then head over to the package manager. Find the 3D game kit and import it into your project. And we really only want Ellen, so you can unselect all of the other characters and then select Ellen to be imported. I also brought the environment pack, but this is totally unnecessary. You can instead just do a few cubes inside of Unity and you'll be totally fine. The reason I made it like this is just because I enjoy working on a pretty level. I find that this is like the Bob Ross moment that you have in video game making, you know, the happy little tree over there, cookie little rock up in a mountain. I don't know, it's just enjoyable. And this one looks like finished up. It's still pretty rough, but not bad for an hour or so of mindless decorating. Now let's go into our assets, 3D game kit, character, Ellen, models, and then drag Ellen into the world. Now we need to create a camera that will look at our character. So let's go into the package manager and change the filter to Unity registry and just search for Cinemachine. Install this. Once it's done, switch back to your scene and you'll see on the top now you have a tab for Cinemachine. So let's select it and let's create a free look camera. This is not really a camera, it's a camera controller. So if you look now in your main camera, you'll actually have a component in it that's called the Cinemachine Brain. This component is essentially just telling your camera, hey, this other free look camera is going to tell you where you need to move to. There are a couple important settings that we need to set up on our free look camera. One of them is the follow, which basically tells the Cinemachine camera what is it going to be following. So we're going to set that to Ellen. And then there's the look at setting. For this, we're going to create an empty object underneath Ellen, and then we're going to rename it into camera look at. By default, the object will be near her feet, which may or may not be what you want to be looking at the whole time. But in our case, we're going to move it near her shoulders. Now we assign it to the camera, and let's give this a try. There we go. Now we have a camera that orbits around. Right now the axes are inverted, which is when personal preference comes into play. So I'm going to tweak a few settings on the camera. First of all, we're going to turn on the save during play. This allows you to make changes to the camera while the game is running, which makes things much easier to preview. I recommend you turn it back off once you're done with your changes, just so you don't accidentally change something unexpectedly. So the couple settings I want to change is I want to invert the axis, and then I want to speed up the movement of the camera. But it's really up to you what you want to do with it. The feel of your camera will be a very defining part of your game. So for example, in a game like The Last of Us, the camera is really close to her and is right above her shoulder. So what does over the shoulder mean in movies, for example? It's very often used in conversations or in tracking shots, and it's essentially what tells you which perspective you're occupying. So by putting the camera there, you're essentially saying, this is you right now. A very different approach is Ratchet and Clank. The game will put you all the way in the bottom of the screen, and then horizontally, you'll be in the center when you're not aiming. And when you're aiming, it will switch you from side to side. So very different feel from the last one. Since Ratchet is much smaller and the view is much wider, it allows you to see enemies coming, and it's much more useful for a tactical gameplay side of things. This on the bottom and centered type of position for your character is actually very commonly used for cars and other vehicles. So it really gives you more the idea of it being something you're using rather than someone you're being, if that makes any sense. Other games like Ghost of Tsushima, for example, will adapt the camera depending on the situation. So for example, here in a one-on-one duel, the camera is really up close, so you can really feel like you're inhabiting the character, and it's a very personal encounter. And then when you fight multiple enemies, the camera actually pulls back and it doesn't track you as closely. So those are just some of the many different types of third-person cameras there are. So now you have to decide for yourself, what do you want? Do you need something that's intimate? Do you want something that's tactical? Are you really in close spaces? Are you in a really open space? Those and many other considerations will influence what the final feel of your camera should be. Okay, so the next thing we're going to do is add some movement to Ellen. So select her, go to add component, and let's add a character controller. Character controller is a Unity class that will allow us to move Ellen around. It has support for things like slopes, collisions, things like that, but it is unaffected by things like velocity, momentum, etc. If you want a more physics-based character controller, imagine for example something like Fall Guys, then you probably want to use a rigid body instead of using the character controller. So now we can see our character controller has this little capsule that it draws around your character. And if we move down, you can see that it's actually going through the ground. So we need to adjust a couple settings. Let's move it up a little bit by 1. Now it's too tall, so let's adjust it a little more. I think it's too tall for this character. She's on the short side, so let's make it 1.7. And then on the Y, let's make it like a 0.85. Now we need something to control the character controller. Who controls the character controller? So we're going to do a new script, call it third person controller. And once it's created, give it the good old double click. This will open your code editor. In my case, it's Visual Studio. And then we'll just delete this comment that I don't need. And we're going to need an access to the character controller. So let's create that. Let's just call it my controller. And then in the start, we're going to say my controller equals get component. And then we just pass in the type of character controller. Now we need to use this. So let's go to an update function and let's get some input. So let's declare float x equals input get axis raw horizontal, and then the same but for Z. The reason we're doing X and Z instead of X and Y, which maybe you would expect, is because if you look at the positions as we move forwards and backwards, we are altering the Z axis, and when we move sideways, we're altering the X axis. If we move Y, we're just moving up and down, which we'll use later for jumping. And if you're wondering where that horizontal and vertical come from, you can go into Edit, Project Settings, Input Manager, and then you'll see there a list of inputs that are predefined by Unity, and you can add your own as well. So here we have our horizontal, which is mapped to left, right, A and D, and vertical, which is mapped to down, up, S and W. Back in our code, now let's make use of that X and Z. So let's declare a vector tree. Let's call it movement, and that's equals new vector tree X, 0, Z. And then below that, let's call my controller dot move, and let's pass that movement vector in there. We go back to our game and give it a test. We'll see that there's one big issue with it. If we press forward, you'll see that we just warped at the speed of light, and then we press backward and we warp again. The reason this is happening is because, as you can see on that comment I left, it says update is called once per frame. So in a computer that's running at 30 frames per second, you'll move 30 meters per second. In a computer that's running at 100 frames per second, you'll move at 100 meters per second. And clearly, that's not what we want. You never want to have things in games that are frame rate dependent, because it's very unreliable. So the easy solution for this is to scale the movement based on the time. To do this in code, we just multiply movement by time.delta time. Delta time will be an amount in seconds since the last frame happened. So for example, in a game that's 60 frames per second, there'll be around 16 milliseconds between each frame, which means time.delta time will give you a 0.016. So it's a very, very small number. So now back in the game, as you can see, if I press back, I move pretty slowly, but it's no longer frame dependent. Obviously, we don't want our character to move that slow. So let's create a new variable called public float speed. And for now, let's set it to 5. Now let's make that do something. And that's very simple. We just go to a move function and we just multiply speed by the movement. Go back to the game. And as you can see, now she moves at a much better speed. Now, a problem you'll see is that if we turn the camera that way and I press forward, she actually moves forward on her direction, not the direction of the camera. So to fix that, we're going to need access to the camera. So let's do public camera, and let's call it my camera. Then down in the update, we're going to declare a vector tree, and we're going to call this rotated movement equals my camera dot transform dot rotation, and we're going to multiply that by movement, and that will basically turn the movement direction into the rotation of the camera. Now this is going to have a problem, but we'll see it in a moment. So let's copy this into here, let's save it, and let's try it out. So back in the game, we select Ellen, and over here we're going to have a slot for the camera, and let's select the main camera and assign it in there. And if we look in that direction and press forward, that's the direction she moves. But as you can see, there's a bit of a problem here. If I look up, she goes up. If I look down, she goes down. That's because we're grabbing the raw rotation of the camera, and we need to only grab the y-axis. So we're going to do some work with quaternions now. Quaternions are a way that Unity and many other engines store rotation information. They're kind of hard to read, so generally what you end up doing is, instead of using the quaternion directly, you turn it into Euler angles, and then you turn those Euler angles back into a quaternion. And Euler angles are pretty simple. Essentially, the rotations on 3 axes. So for example here, if I grab this one and I start rotating, it'll go rotation on the x-axis. And then if I select this other one, I will rotate on the y-axis. And finally, the last handle will rotate on the z-axis. So back in the code, instead of grabbing the full rotation, we're going to cut this. I'm going to say quaternion dot Euler. And then we're going to pass 0 for x. We're going to put this rotation here dot Euler angles dot y, which is the one that we actually care about. And finally, we're going to pass 0 for z. So back in the game now, if we press forward, we move that direction. And if we look up and we press forward, we're still just moving on the floor. So now we got another interesting decision for how we want to make our third-person controller. For example, in a game like Fornite, you'll see that the character is always looking in the same direction that the camera is facing. So as I turn my camera around, as you can see, my character also turns around. And then if I want to move sideways or backwards, she'll just run a strafe animation. On a different style, on Warframe for example, if I move forward, I'm going with the camera, but I can also start just moving independently from the camera. So as you can see, I go sideways, I even can run directly into the camera. So that basically makes it so that I can move in a different direction that I'm looking. In this case, we're actually going to do the version closer to Warframe, mainly because the asset that we have does not have any strafe animations. So back in our code now, what we need to do is basically convert our movement vector into an angle. And to do this, there's a trigonometry function called a tan2 that we can use. So basically we do float angle of movement madf.atan2, and then we're going to pass rotated movement.x and rotated movement.z, and this function will actually return radians. So we need to convert it to degrees, which we can easily do by multiplying by madf.rat2deg, which will give us a conversion. And then we're going to set transform.rotation equals quaternion.Euler. And we're going to pass 0 for x, and just like before, we only care about y, so we're going to pass angle of movement as y, and then 0 for z. So now we get here, and then when we press forward, you'll see we do this crazy spin. Same when we do sideways. The reason why this is happening is basically we're saying, let's rotate our character based on the movement, and the movement is rotated based on the camera, and the camera rotates based on the character. So it's creating essentially a loop of transforms there that, as you can see, goes pretty crazy. So the solution for this is extremely simple. We just go into our free look camera, and down in the settings there will be a binding mode that says lock to target with world up. Instead of that, we're going to change it to world space, Now we press forward, she moves forward. We press sides, she looks to the sides. So that's pretty good. One issue she still has is that whenever we let go, she turns back to her original position. So let's give that a fix. To fix that is extremely simple. We're just going to say if rotated movement dot magnitude, which will tell us how much it's moving, is greater than 0, then actually do this part that does the rotation. Otherwise, don't do it at all. And now when we let go, she just stays in whatever rotation she was at. It doesn't look great that she just snaps into that rotation, so let's smooth that out. So for that, we're going to create another variable here, and we're going to call it float desired rotation. And let's set it to equal 0 to begin with. So instead of doing just a temporary variable, we're going to set this to our new desired rotation. Same with this one. And we're going to move this outside of the if, because we do want to just change the desired rotation when there's a magnitude, but we want to keep updating the rotation even when there's not. So let's declare a quaternion. We're going to call this current rotation, which is going to be equal to transform dot rotation. And we're going to declare another one, which is going to be quaternion target rotation, which is going to be equal to what we have right here. So instead of setting the target rotation directly, we're now going to make it smooth by using quaternion dot lerp. Lerp stands for linear interpolation, and you can do this for a lot of things. You can interpolate between floats, you can interpolate between vectors, quaternions, colors, so on and so forth. And we're going to pass here our current rotation, and we're going to interpolate into our target rotation, and then we need to tell it how much do we advance there. And for that, we're going to create a new variable that we're going to call rotation speed. And just like we did for our other speed, the movement speed, we have to multiply this by time dot delta time so that the rotation works with any frame rate. So let's grab this one over here and let's declare it as a new parameter. So public float this, and let's set it to 15 to begin with. So now when we move, as you can see, she turns in that direction instead of just snapping, which looks much nicer. So one thing that's left to do is, this is my movement if I move forward and backward. Then this is if I go sideways. If I go diagonal, I actually move faster. So now we need to do a little correction. If you press forward, you can see it advances instead by 1. If you press to the side, it advances on X on 1. But if you press both, it will actually add 1 on each axis, which ends up being 1.41. And this was called the strafe running back in the days of Doom. And that is actually very easy to fix. All we have to do is in the movement, we need to select over here and set it to normalized. And what that will do is, no matter what values you have in X and Z, the vector will always turn into a length of 1. Okay, so I don't know about you, but I'm ready to move on from the T-pose. Time to add some animations. So first of all, select Ellen and then go to her animator and turn off apply root motion. What this does is make the animations actually move Ellen around. Since we're using code to move Ellen, we don't want that. Then we're going to go into our assets and let's create an animator controller and call it whatever you want. Let's go back to the animator and select on the controller and select the animator that you just created. Now double click your animation controller to open it up. It's pretty barren at the moment. So right click on the stage, create state, empty. And let's not name it for now. We're gonna select on the motion. This will give us a list of all of the animations that we have. So let's look for idle and select that one. And when we run the game, you can now see she has an idle animation. So let's stop the game, get back into the animator. On the left side, you'll have a panel that has layers and parameters. So switch to parameters and let's add a new one, float, and let's call it speed. And let's go back into the state we created and let's rename it into movement. Then right click on the state and say create new blend tree in state. And a blend tree is basically something that will allow us to combine several animations together. In this case, what we want to blend together is the idle, the walk, and then the run. Now you can double click on the state to go inside and look at the blend tree. And if you ever want to go back, you can use the buttons on the top left. The blend tree will already have the speed attribute associated with it because it's the only float attribute we had. In the properties, you can see there's many different types of blend trees. In this case, we want a one-dimensional blend tree. Then down in the motion, we're going to add a motion field for each one of our animations. So click on it, select idle, then select the walk, and finally select the run. And you can see at the end, it has thresholds that it pre-assigned. You can also set this manually, but the automatic ones in this case, we'll just set it to 0, 0.5, and 1. The thresholds are what it uses to determine which animation to use. So, for example, here we can start moving the slider, and you'll see when we're at 0, we're totally still. And as we move towards the right, towards 0.5, she starts moving a little bit. And eventually, if we get all the way to 1, she'll start doing like a full sprint. Okay, now we need some code to actually make use of that. So let's declare over here an animator, which is what we need access to. And let's just call it myAnimator. And then in the start, we're gonna just call myAnimator equals getComponent, and then just pass in the type animator. Then to use this, down in the update cycle, we already had a check there to make sure that we were actually moving by checking the magnitude of our movement. So in there, we can just add a call to myAnimator.setFloat, and then we're gonna pass the ID that we set, which is speed, and then we're just gonna set it to 1 for now. And then we're gonna create an else saying if we're not moving, then set it to 0. Let's give it a test. We're standing, and then if we press, we start sprinting, but as you can see, it is an immediate jump from 0 to 1, which doesn't look particularly good. So what we want to do is actually smooth it out, kind of like we did with the rotation. So let's declare m desired animation speed. And then in here, instead of doing this call directly to the animator, we're just going to call m desired animation speed equals 1. And similarly on the else, we're going to say m desired animation speed equals 0. And then we're going to move this call over here. We're just going to recycle it. And we're going to replace the passing of the number directly. And instead of that, we're going to call a lerp. So lerp is just going to get us a value between two other values. Our first value is going to be what the current speed is, which we can ask the animator what it is by saying myAnimator getFloat speed. And then our second value is going to be our desired animation speed. And last but not least, we need to pass in the value to determine where in between those two values do we want to be. And for that, we're going to declare an animation blend speed. And just like we did before, we need to multiply this by time.delta_time. And then we're going to go up here and declare it as a public float animation blend speed and give it a default value of 2. So when we press forward now, you can see it smoothly goes from standing still to sprinting, maybe a little too smooth. So I think right now we left it with a value of 2. So let's go into our settings and change it to maybe a 6, and let's see how that feels. That's pretty good, but you can adjust this as you wish. The next thing we want to add is the difference between running and sprinting. So let's copy speed and let's create a new one called sprint speed, and then let's change the base speed to like 2 or something. Then now here, let's declare a boolean and let's call it m sprinting, and by default set it to false. Then in the update, we need to read the input. So let's declare m sprinting equals input dot get key. And we're going to use the key code left shift. Then down below where we do the move, we're going to replace speed with m sprinting question mark and then m sprint speed and then a colon and speed. If you haven't seen the question mark and colon syntax before, that's called a ternary, and it's essentially a way to write an if in a single line. So essentially the question mark is saying, if m sprinting, then do the first one, else do the second one. It is pretty convenient. I personally love ternaries. Then down here, when we're doing the desired animation speed for moving, we're going to do exactly the same. And sprinting question mark 1, else let's going to say 0.5. So when I press forward, I start walking. And then if I press shift, I can run around. Okay, so now that we have the basics in, let's do some jumping. But before we do, if you ever want to watch more of my content, I stream on Wednesdays, Mondays, and Saturdays. I don't know why I set them out of order, on twitch.tv/PabloPoon. And it's basically kind of like this, except a little more random and chaotic. The first change we need to do for jumping is that currently she defies gravity. So she can go up, but she will never fall down. So to make this work, we need to create a couple floats. One is m speed y, and we're gonna set it to 0. And the other is m gravity, and we're gonna set it to minus 9.81f. It's a pretty well accepted constant for gravity, but if you want your game to feel more floaty, or maybe you want it to feel heavier, you can totally tweak that. Then down on the update, we're gonna declare m speed y plus equals, and then we're gonna set gravity times time dot delta time. And we're gonna create a new vector for our vertical movement, and we're gonna set it to vector.up, which is basically just a vector that's pointing up on y, and we're gonna multiply that by m speed y. Then in our move code, we're gonna add this new vertical movement that we just added. So we add a parenthesis, vertical movement plus, and another parenthesis, and we just put all our current horizontal movement in there. The reason why we separate it with parentheses is because we don't want our vertical movement to be multiplied by our sprint. Essentially, we don't want to jump higher because we're sprinting. So now let's test again. When we walk off the cliff, now we fall. Excellent. Now we fall pretty fast. The reason for that is that if we look at our current value for m speed y, which we can do by going into our menu and setting the mode to debug so that it shows us all our variables, we can see that m speed y keeps getting lower and lower and lower and lower even when we're standing on the ground. And this is just because gravity right now is not checking to make sure if we're on the ground or if we're in the air. Character controller already has a check for this, so we can check if not my controller dot is grounded, meaning we're in the air, then make sure that gravity is applied to our speed y. Otherwise, let's reset our speed y back to 0. When we go to test this, there's not a lot that we can see that has changed, other than the fact that the variable is now resetting. But on other occasions when I've done character controllers, this problem actually has been bigger, and it's caused me to be unable to move my character at all. So depending on the settings that you use, you might be running into that problem. So to set up for jumping, we're gonna need a few things in our animation controller. First, let's create a float and let's call it speed y. This is gonna be our vertical velocity. And then we're gonna create a couple triggers, and this will be like one-time events that happen whenever you trigger them. The tree will basically see that the trigger is on, consume it, and turn it off. So we create one for jump, and then we create one for land. Then we're gonna create a new state, and we're gonna call it jump. And just like we did with the movement one, we wanna convert this into a blend tree. We're gonna change the parameter from speed into speed y. Then we're gonna add a few motion fields. We're actually gonna need quite a few here. So when we go into selecting, we can look for jump, and you'll see there's 6 different clips. We're actually gonna want them all. You don't need them all, but the more you put in, the better the blend will look. So I'm just gonna quickly add all 6 of them. So the default thresholds for the blending are from 0 to 1. In this case, we want to change them to be from -1 to 1, which basically will mean at 1, you'll be when you just started jumping. So your velocity on y is at its biggest point. And then as you start going up, gravity will start slowing you down. When you reach the peak, that will be 0. And then when you start going into the negatives, that means you're now falling until you get to -1, which is when you're about to touch the ground. So I'm going to disable the automatic thresholds, and then I'm just going to set values from -1 to 1. And I recommend once they're in, maybe just pause and copy the values that I have there. And let's take a look at how this works. So here you can see this is the animation for jumping. If I'm at 1, she's actually sort of lifting up, arms down. So basically this is when the jump is just starting. And then as I start moving the speed y, you can see she goes into that state, which is like the peak state. And if I continue, now she's falling. Go back to the base layer. And let's create a transition from movement into jump. And we're going to turn off has exit time. This is so the jump animation starts right away and it doesn't wait for the walk animation to be done, because otherwise it will feel kind of laggy. And the conditions, we're going to add a new one and we're going to set it to the jump trigger that we added earlier. Now we're going to create a new state, and this time I'm going to create it as a substate machine. And a substate machine is essentially what we've been doing here, which is a series of nodes that connect to each other based on states, but it's inside. So almost imagine it as a folder to contain more nodes inside. Just a way to keep things organized. So let's rename it into land and then double click on it. And now we're inside. And as you can see, it looks pretty much like our state looks outside. Then we're going to create a new state, and we're going to create 3 states here. One for land run, another for land walk, and last for land idle. Then we're going to add animations to each one. So let's select land run again. And the animations are going to be all called land. There's 5 of them, so just avoid the ones that are called fast. And you can see the ones I selected here and just copy those. Then we're going to make some transitions. So let's go from entry, make transition into land run. This one is a special case because it's the default transition. So when you select it, you also have to go in the inspector and click on animation transition so that you can modify the transition. And on here, we're going to add the condition to be speed greater than 0.51. So essentially, if our speed is beyond the 0.51 point, we're going to run the animation for landing while running. And similarly for land walk, we're going to add one, but this time it's just going to be greater than 0.1. And for land idle, we don't need to define a condition, since basically it will be the one it will use if neither of the other 2 are met. Now we're going to transition out of our substate machine and back into our base layer. So for that, we're going to create a transition from each one of the landings back into the base layer. So you just say make transition, and then state machine, base layer, make transition, state machine, base layer, and basically just do it for all 3. Back in our base layer, we're going to make a transition from jump into land, then selected, and we're going to turn off the exit time. This is because we want the land animation to run right away. And to the conditions, we're going to add it to be on the trigger of land. And then we make a transition from land into movement, and that one doesn't need any special settings. And that's it for the animation tree. So let's do some coding. The first thing we're going to do is create a bool over here, and we're just going to call it mJumping, and we're going to set it to false to start. Then in the update function, we're going to check if input.getButtonDown jump, and we're not already jumping, then we're going to set mJumping to true, and then let's call myAnimator.setTrigger jump. Then we got to do the actual jumping, and for that we're going to do m speed y plus equals, and then we're going to call this jump speed. We haven't declared this variable, so let's copy it from here. Let's take it to the top and let's put it among our other variables. Public float jump speed, and let's set it to a default of 15. Now we need to inform the animator about speed y, so let's say myAnimator.setFloat speed y, and then we're going to pass m speed y divided by jump speed. And the reason we divide it is because if you remember earlier from when we set up the blend tree, we set up our values from -1 to 1. So we want to pass a proportion of the speed on y rather than the actual speed. And now we want to detect if we landed. So for that, we're going to say if mJumping and our speed is less than 0, meaning we're falling, then we want to do a raycast from our feet down to see if there's anything we're about to collide with. The reason we do it with a raycast and not just when we touch the ground is because we want to start running the animation a little bit before you land. This will help make it feel a little more organic. If you run the animation for landing after you landed, it looks a little bit stiff. So for this, we're going to declare a raycast hit, and we're just going to call it hit. And then we'll say if physics.raycast, and we're going to cast the raycast from our feet, which is basically at transform.position, which is at the very base of our character. And then we're going to make the raycast go down, which we can pass in with vector3 dot down, and then we're gonna say out hit, which is the hit that we just declared, and that's gonna save the information about the raycast hit, which we're not really gonna use right now. And then we're gonna say 0.5, which is the distance. We're gonna say check half a meter below our feet. And then we have to say what are we gonna check the raycast against. And for now, I'm just gonna set the layer mask to be the default one. And in here, we're gonna declare end jumping equals false because we just landed. And we're gonna say my animator dot set trigger land. One issue that can happen right now is that we could jump, and then if the game decides we're on the ground, which makes sense, it would actually reset DM speed Y back to 0. So in here, we need to check that it only resets back to 0 if our speed is actually less than 0, meaning when we're falling. Okay, let's give the jump a test. Whoa, okay, maybe that's a little too much. So let's go into our settings and let's change the speed from 15 to like a 7 maybe. Yeah. And let's see how that feels. There we go. That seems better. Obviously you can make this as high as or as low as you want. And you'll just have to adjust that number and probably also adjust the distance that we do the raycast from. And we got it. That's a wrap on the third-person controller. So what's next is totally up to you. My recommendation would be grab what I showed you as a foundation and then just twist it a little bit. So for example, you could add a double jump. You could grab the assets from the package and just try and make the turning a little smoother because right now it's pretty janky. There's all sorts of things that you can do. I find that doing those sorts of things is where I at least learn the most. So hopefully that works for you as well. And with that, I hope you had a good time. Hope you learned something. I'll see you next time. Adios.
Well, thanks for stopping by. Don't forget to like, subscribe, and hit the bell to be notified when new videos come out. Thanks for watching.